So, we'll start the afternoon session with Fotis Farakos from the Technical University of Athens, who will talk about the sitter vacua, Soplant, and supergravity.
Thanks. Let me check the thing. Does it... Από εδώ μόνο? Εντάξει, okay. So, first of all, thanks a lot for the invitation. Yesterday was really amazing also to see the younger researchers. Also today has been very interesting as well. So my talk will be about some work I've been doing the last couple of years, but also some ideas generically that I have about the topic. And it has to do with the sitter vacua, swampland, and of course supergravity. The plan of the talk is the following. So first I will give an introduction where I want to motivate why I am interested in this topic. And during the introduction, I will highlight two specific aspects that I want to focus on, which will be the gaugings of supergravity and nonlinear supersymmetry. And then finally, of course, then I will analyze these two things, and then I will conclude. So let me start with the introduction. So the problem, first of all, if I keep it like this, the microphone, you can still hear me, right? I don't need to have it in the, all right, very good. So let me start with so what is the problem that we have? Well, the problem is the following. Currently, the way things are, it seems that our universe is described by some form of dark energy. It is important to highlight that actually, even from phenomenology, we do not know if the dark energy is some time-dependent cosmological constant or if it is a fixed cosmological constant. This means that even when we are struggling to find the sitter vacua, it might be that actually we don't need them because who knows, in a billion years we find out, oh, the cosmological constant is changing. All right, so we should keep this in mind when we are doing these discussions. Of course, obviously, the sitter is in some sense very important and very simple to understand it conceptually, at least classically. And therefore, of course, the first thing you ask is, okay, let me just find the sitter and then I move on. Well, it turns out that if you try to find the sitter in string theory, it is extremely difficult. There is an understanding partially why this difficulty is there and why it should be there and why you better find the difficulty when you are trying to find the sitter. However, there are instances where there is also a building consensus that it might actually be impossible to find the sitter. But this is all sort of an open discussion. I mean, it's not clear what is going to be eventually the answer. The certain thing is that there is I think everyone agrees that the sitter is something very difficult to track down, and it's not going to be in a regime in string theory that we are going to be able to understand with full confidence. Now, from my perspective, I mean, of course, I'm interested in finding the sitter in string theory as it is. However, there is another way that we have been understanding the vacuum structure of string theory over the years. And this has to do with studying four-dimensional supergravity, n equal 1, n equal 2, and so forth. And supergravity has the advantage that actually you have, first of all, it is a field theory, coupled to gravity, but you have specific ingredients that you can work with. The superpotential, and these ingredients are very few of them actually. The superpotential, if you can have one in n equal 1. Then there is the so-called gauging. I will show what it is. It is a terminology, but you will see what gauging means. And then there is nonlinear supersymmetry. All of them are important. We use in string theory, you find them all the time around the place. And but from the supergravity perspective, if you don't know where these ingredients come from, it is up to you to choose them. And of course, since you can choose them to be anything you want, you can do anything you like. So there is almost no restriction when you are trying to construct specific vacuum and supergravity. There is almost no restriction what you can do. You can do anything you want, more or less. Especially if you break supersymmetry, you can go out of control. Now, the question that, of course, this difficulty has been troubling everyone since we understood that there is a connection between string theory and supergravity. And an idea of maybe trying to approach this problem is to try to use supergravity, but take as input restrictions that come from the swampland. And there are all sorts of restrictions that can come from the swampland. Some are more bold, like the de Sitter conjecture. I will discuss it only for a bit. But some are more established, like the weak gravity conjecture, the no global symmetries conjecture, and so on. Here, I will take for granted the most established swampland conjectures, the ones that we think that we understand and that we trust more. Thankfully, we heard a lot about the swampland yesterday, but of course, still I will give a very short introduction. The idea of the swampland is that, as an idea, actually, I would say it should be obvious to any physicist. The idea is that not any effective field theory that you write down can be embedded into quantum gravity. This is the trivial part. The highly non-trivial part of the swampland is to find how you know which theory can be embedded and which not. And how do you express this in mathematics and not in just words that we say to each other. And I will show you some formulas in a bit. So the idea is that, okay, not all field theories, not all effective field theories that include gravity can be embedded in quantum gravity. And how do we know who is who? We have the so-called the swampland, and the idea is that the ones that cannot be lifted to full quantum gravity belong to the swampland. And what are the rules? The rules are some rules that we guess by looking at common properties of string theory vacua, or from expectations that we have about quantum gravity, and then we go test these things, and then we figure out some basic rules. So for me at least, the most personally, really something that is interesting for me is the weak gravity conjecture, my favorite swampland conjecture if you want. And the idea, and this is how you express it in mathematics, it just tells you that if you have a theory of gravitation that has inside it electromagnetism, naively you would say, okay, my cutoff is M Planck, because what can electromagnetism do? However, that is not actually true. Your cutoff can be actually parametrically below M Planck, because according to the swampland, your cutoff is below G times M Planck. So if you are at weak coupling, which counterintuitively you would think, okay, the weaker the coupling, the better. Actually, that's bad for you, because it means that your cutoff is coming down. And actually, this conjecture, this is a version of the weak gravity conjecture that I have on the slide. It has this is the so-called magnetic version. There is an electric version, but let's focus on this one for simplicity. And then there are, of course, other swampland conjectures. The one that tells you that if you have a non-supersymmetric vacuum, then somehow it has to have a decay channel. That is what the conjecture is telling you. Of course, it was first studied in ADS, but essentially, if you believe it in ADS, it becomes obvious for de Sitter. And then finally, there are many more swampland conjectures, and very interesting also. But on the bottom, you can see one of the more bolder ones that tells you that actually, if you have a field theory with a de Sitter vacuum, then it is in the swampland. It's as simple as that. This is something that I believe is quite deep. Maybe it sounds too bold and too naive, but I think I wouldn't just exclude it as something very simple. All right? You talk about stable de Sitter. Yes, metastable de Sitter vacuum, of course. Metastable de Sitter vacuum, always metastable de Sitter. And that is actually one of the central differences of finding a de Sitter in string theory, because we are always talking about metastable ones compared to any other field theory. Because of you mean tachyons? There is no problem with that, but still yes. That is a very good point. So when this paper first appeared, actually they excluded any type of, they said also tachyons are not allowed. And for me personally, that was fine, actually. I cannot see the difference of having the metastable one and saying, well, okay, no, it can be tachyonic. Okay, if one happens, also the other has to happen. But then they revised it and they said, okay, no, well, okay, you can be metastable, so there can be also not, you can have tachyons. It's a big discussion, and this is something very interesting, but I will not go more into that for the moment. I will stay to the conjectures that we mostly understand, the weak gravity conjectures and so on. So let me start from the, as I said, I will focus on the weak gravity conjecture and the condition that when you are breaking supersymmetry, you have to decay. The first one, because it includes couplings to electromagnetism, is related to gaugings, what we call gauging in supergravity. So now we'll turn to de Sitter vacuum and supergravity that can be constructed from gaugings. And I will show you how we can, by using the swampland, we can understand how catastrophic its effects can be when we are trying to find de Sitter vacuum supergravity. So the first thing we learn when we start to do supergravity is the Fayet-Léopold, when we start to do supersymmetry is the Fayet-Léopold term, and then of course we embed it in supergravity and we realize that it is the easiest possible way to get a de Sitter vacuum in supergravity. There is nothing easier than that. You take supergravity, you include U1, you include electromagnetism, and then all you have to do is just charge the gravitino under the U1. Once you do that, you get a de Sitter vacuum. Is the first thing you learn. And of course, because of the simplicity of this construction and because it gives you automatically de Sitter vacuum supergravity, is one of the reasons that people have been trying over and over to construct such things in string theory. And of course, no one ever did it. And you can ask yourself, okay, why can this be happening? And the answer actually comes from the weak gravity conjecture. Because what happens is that you can see that you have a U1 and the gravitino is charged under the U1. And because of that, this automatically defines a UV cutoff according to the weak gravity conjecture. And the UV cutoff is G times M Planck. Here psi is the gravitino charge, you can put equal to N, doesn't matter. So you see that according to the swampland, you have a cutoff that is given by G times M Planck, or psi, if you put psi also, if you want. But in the meantime, the de Sitter vacuum that you are constructing has a Hubble scale that is given again by G psi M Planck. So what is happening here is that you have a situation where your Hubble scale is of order of the cutoff. And this, of course, in a de Sitter vacuum is catastrophic. Okay, it means that you cannot trust it at all. But also, if you are aware of the Dine-Seiberg problem, it tells you that actually this de Sitter vacuum is living in a region of string theory that is very strongly coupled. And this is, of course, the Dine-Seiberg problem. So in this way, we can start getting intuition about the problem of finding the de Sitter vacuum in string theory in weakly coupled regions just by looking at supergravity and combining it with the swampland conjectures. Now, this is a very simple example. This is actually work we did with George Rigas and Niccolò Cribiori. For me personally, this is when I started to be interested in the swampland, once I noticed this coincidence. And of course, then later, yes? To lift the de Sitter vacuum. No one knows the lift. That's the problem. I mean, it looks easy, and then you say, okay, let me do it let me derive it from string theory. But when you try to do it, the usual problems show up. I mean, you are full of problems. That is wrong, actually. This is a paper by Komagorski and Seiberg that you are referring to. Yes, we have shown that actually R symmetry is not there. It's not you can break it by higher order terms. So Now, this was n equal 1. You can do the same thing. You can put them. You can also put them in the superpotential if you want, or the Keller potential. But yeah, but of course, higher derivatives also if you want. There is infinite terms that you can write down that break the R symmetry. This was something that was troubling me for years, and then actually in the end we realized that supergravity does not give you this restriction at all. So then you can go and do something similar in n equal 2. Here I will start with a simple n equal 2 example. It is tachyonic. Forget about the tachyon for the moment. We will treat it in a bit. The construction here has standard n equal 2 supergravity, which of course contains also a vector inside it, the graviphoton. And I include one more matter multiplet, which contains a matter vector multiplet. So it contains one more vector. And the idea, again, is to charge the gravitino under the two vectors. Psi 0 corresponds to the charge of the gravitino under the graviphoton, and psi 1 corresponds to the charge under the vector field of the matter multiplet. Now, if we put psi 0 to 0, and we keep only psi 1, so we charge the gravitino. Actually, these are two gravitins. Okay, we charge the gravitino under the vector of the matter multiplet. Then we get again a potential that has a de Sitter critical point. It is tachyonic, but forget that for now. The point is that even that critical point, you can see that it has the vacuum energy given by G. Here, okay, I'm putting m Planck equal to 1, so the vacuum energy would be G square Q 3 half square times m Planck to the 4. So the Hubble scale will be again G, Q, and Planck. But we already know that G, Q, and Planck is the UV cutoff according to the Swampland, to the weak gravity conjecture. So once more, before you worry that such a critical point is tachyonic, you realize that actually this critical point does not even exist, because you are at either you respect the Swampland, so your theory is strongly coupled, so you have no control of this background, or you say, no, I'm not in the Swampland. Well, no, or you say, I don't respect the Swampland, but then, okay, you are in the Swampland, actually, so it's problematic. That's a very good point. If you are supersymmetric, of course, things are very nice, but if you don't have supersymmetry, yes, you need other methods, but yeah. The other amazing result that you can draw from this discussion is that if you turn on the coupling with the graviphoton and you switch off the coupling to the matter vector, then you get SUSY ADS. And what happens there is that you realize, exactly due to the same construction, that your cutoff is as big as the ADS length scale. There, because you have supersymmetry, you are fully controlled, and this is what happens in many of the holographic scenario. And this is actually a result that Niccolò Cribiori did with, where is this? Yes, with Gianguido Dall'Agata, and they saw that actually you cannot have scale separation where if you are in n equal 2 or more. If you are on SUSY ADS, of course, all right? I don't know, actually. Yeah, that's a good point. I only think of electric because I want to do the weak gravity. That's a good point. Now, as I promised, you don't have to worry about the tachyon. And the reason is that with a series of 2 publications we have to write to cover all the cases, we have shown that even if you look one by one the models that are not tachyonic, and you are in 4D n equal 2, you find that all the constructions have exactly the same problem. Your Hubble scale is as big as the cutoff. And because you are in de Sitter and supersymmetry is broken, you are done. Or, in some sense, it is telling you that you are really finding the Dine-Seiberg problem. The Dine-Seiberg problem is all the knowledge that we have that the hope of finding de Sitter in string theory is in regions where you are not weakly coupled. And you are rediscovering the same problem again, but using only supergravity and the Swampland. Is the GS. Yes, Now, the other interesting thing about the swampland is that many times, especially when you are within the validity of supergravity, you see that various swampland conjectures start to talk to each other and start to give you the same results. Like here, for example, the weak gravity conjecture tells you that you cannot have a de Sitter, actually, just like the conjecture of Baffa and et al. All right. Also, what happens here is that exactly that this vacua would violate the so-called Festina-Lente bound, but actually the weak gravity conjecture eliminates this vacua, and indeed the same vacua would be in contradiction with the Festina-Lente bound. So both conjectures lead to the same results. You cannot have such de Sitter vacua. And of course, one of my interests is to study other couplings of supergravity, like Yukawa couplings, magnetic moments, and so on, and see what type of swampland conjectures apply to them, and then use them to restrict the vacuum structure of supergravity. They are asking that actually if you have a very big black hole in the Sitter, the Nari black hole, you make it as big as you can. They ask that it will not decay, and it's right because it starts to decay, of course, right? The idea is that you don't, and so you have the horizon, and then you have the de Sitter horizon, the black hole horizon inside, and then the de Sitter horizon outside. So they want to avoid the situation where it decays too fast, and then yeah, your black hole horizon passes the other one, and so. Yes, so you are before there. You are before. Yes, but you want to avoid the two horizons to cross. So you want it to decay, but not too fast. That is why they call it Festina-Lente. It's not supersymmetric. It's not supersymmetric. No. Oh, I don't know if it is extreme. Thanks. 10 minutes, okay. I will go a bit faster. Now I go to nonlinear supersymmetry. So another point that comes, as I said, another interesting aspect of one other idea of the swampland is that anything that is not supersymmetric should decay, right? But then when we study nonlinear supersymmetry, what happens is that we realize that the order parameter of supersymmetry breaking is a fixed constant. And because it controls the coupling of the Goldstino, you cannot take it to zero continuously because you will enter a regime where you are strongly coupled. So a question is, well, how does that thing decay? So let me first motivate very fast why this is interesting, because one way to build the Sitter vacuum string theory with all the problems that they have, all right, with all the problems, one way to build them is to start from SUSY ADS, and then include inside there what is called the anti-brane, which in the supergravity regime, one way to describe it is by using the Volkova-Kulov model. So just nonlinear supersymmetry. So you put something in the system that has positive energy and just leaves you from ADS to de Sitter. Of course, there is no microscopic derivation from this. This is just effective theory that you are using to do it. And the idea now is that, well, okay, since anything that is non-supersymmetric should decay, how does the Goldstino decay? So to discuss this, let me focus a bit more on the properties of the Goldstino. The idea is that we can describe the Goldstino with a so-called nilpotent superfield. This is a standard chiral multiplet, the one you know from Wessenbagger, for example. And but on top of that, you put a condition on this chiral multiplet that it is nilpotent in the sense that when you square it with himself, it gives you 0. And this has the following property. So first of all, you can see how the chiral multiplet is the one you know most of you are familiar with. A is a complex scalar, G is the Fermat, and the F is a field that is not propagating. It's just auxiliary. You integrate out. And the interesting the condition x squared is 0 is interesting for the following reasons. If you are on a background that breaks supersymmetry, then the auxiliary field F gets a non-zero wave, and this means that the condition that you have to do, the solution for the nilpotency constraint is given by removing the complex scalar A and replacing it with G squared over 2F. This is enforced on you if you want to respect the supersymmetry algebra. On the other hand, if you are on a vacuum where supersymmetry is restored, the auxiliary field of F gets a zero wave, and then you are forced to solve the constraint by just saying that, by just setting X is equal to 0. And when you are on the vacuum where X is 0, there is this multiplet describes nothing, it is just empty. Whereas when you are on the vacuum where F is non-zero, where the wave of F is non-zero, it describes the only physical degree of freedom it describes is G, the Goldstino, and that is all it captures. There is no fundamental scalar in the theory anymore, at least perturbatively. So here is the puzzle once more. So okay, we know that we like, we know that we can trust the theory when the order parameter F is finite, the order parameter of the supersymmetry breaking. Square root of F is the supersymmetry breaking scale. And of course, we would like to restore supersymmetry, which means we want to pass through regions where F is very small and arrive at F being 0. And clearly, in an EFT, it is highly non-obvious how to do this. And one way that we found that it is possible to describe this transition is to exchange the auxiliary field F of the Goldstino multiplet with what we call a flux. So you change this scalar F with star dC3. C3 is a three-form potential. And star dC3, because we are in 4 dimensions, is essentially a scalar. And this can be done supersymmetrically. So there is a full construction of supersymmetry behind it. It can be done. I will not show it now. And then the next step is to couple this C3 potential, actually to couple a supermembrane to the C3 potential. And the supermembrane can have some charge Q. And because when you are, so this means that if you have a membrane, when you are on the sides of it, the flux value, so star dC3, will take different values depending on the charge of the supermembrane with respect to the C3 potential. And if you want to have a situation where on one side you are breaking supersymmetry and on the other side you are restoring supersymmetry, it means that you have to choose the charge of the membrane to be equal to small f. This is a choice you have to do to decay to decay just using one membrane. All right, it's a choice. If you want, you can put some other value, but if you want to do the decay in one jump, that's it. And of course, the supermembrane has some tension, T3, and that tension also defines another scale in your theory, which I will call here small m. This small m is also important for physics because it describes the strong coupling scale of the nonlinear supersymmetry living on the supermembrane. Okay, I'm hiding a lot of supersymmetric stuff here. I just want to show the physics. So then what happens? Okay, so let me show you very fast. Yes, I will make it. Let me show you very fast how this looks. So you on the bulk. Okay, so you have supersymmetry broken, and then you have a small bubble of a supersymmetric vacuum. All right, so you are in the sitter. Supersymmetry is broken, and then you have a small bubble of the supersymmetric vacuum. And because of the charge of the supermembrane under the C3, inside the wave of the auxiliary field F is completely eliminated, and you are restoring supersymmetry. All right. Outside, you have just a Volkov-Akulov model. Okay, and whatever else you had before that you were lifting to the sitter. And of course, the decay time of this thing depends on the tension and the charge. And generically, it can be long-lived. I don't have an argument to explain why this de Sitter vacuum would be short-lived because of this transition. However, one very peculiar property of this construction is if you ask that the supersymmetry breaking scale on the de Sitter vacuum is the same as the supersymmetry breaking scale that controls the nonlinear supersymmetry on the wall volume of the supermembrane, then the decay is very fast because you just use the usual Brown-Teitelbaum formula, and when you insert these ingredients there, you see that the decay is extremely fast. If you do this small assumption, which is unclear to me if you should do it or not, but generically the decay will not be fast. Still, there is this small interesting, I think, there. And of course, once you do this assumption, you also realize that you are satisfying automatically the weak gravity conjecture for the membrane, which is again another coincidence somehow that appeared. So let me conclude. The question that I wanted to discuss is, first of all, we have the difficulty of finding the Sitter vacuum in string theory. What if we can see this difficulty or build some intuition about this difficulty by looking at the de Sitter vacuum supergravity, but using Swampland conjectures that we understand to restrict them? And we see that we can start to find these small problems. And I have discussed nonlinear supersymmetry. Nonlinear supersymmetry can have decay channels. I have discussed the various problems that you find when you start to study gauged supergravity and the de Sitter. And then finally, I didn't say anything about the superpotential because for the moment we don't have any restrictions for the superpotential. So this is, I think, a very interesting question. What Swampland conjectures can affect the superpotential, and how can we restrict the vacuum structure of supergravity with them? Thank you.
Thanks. So, questions? Yes.
There's an older string theory result which says that supersymmetry is restored always at the infinite distance in modular space. I don't remember how general this is, but that means that the two theories, supersymmetry and non-supersymmetry, one believes in different patches of the vacuum theory. How does this fit with your discussion?
Yes, that's a nice, actually, right, very nice question. So, indeed, in one way to think of it, let me go actually here. And actually, this may be where the Dine-Seiberg is based. Indeed, one way to restore supersymmetry is if you go to infinity. You are not granted to have that. It's not going to happen always, but it can happen. For example, but on top of that, you can imagine that you are in a situation where you have like the KKLT, right? Where you have some SUSY ADS, which is the blue line here in the slide. Forget the other lines. It is the blue line. The blue line is the KKLT ADS vacuum. And that one is in finite distance. And the scalar, there is this scalar, phi. Massless, you mean? No potential. Oh, yes, I'm thinking about moduli stabilization. Yes, yes. But still, I agree with you. Yeah, I mean, I'm thinking of moduli stabilization. But here, though, if you think of the KKLT for a bit, you see that still the blue line, when you take phi to infinity, goes to 0, right? You get Minkowski. However, that limit does not restore supersymmetry. Of course, first of all, you stop to trust a model when you go too far, because in ADS you have supersymmetry. But I'm saying that if you take the scalar phi and you follow the potential to infinity, supersymmetry is not restored. You just get a no-scale model. So you could expect that if you want to restore supersymmetry, the two limits would be very far away. So there is no way actually with you can somehow trust the tunneling between the two. But here in KKLT, the vacuum are not far away. I mean, the golden line is the de Sitter vacuum, and the other is and the blue line is the ADS vacuum. So it's not always like that.
Other questions? Yeah, go.
I'm just wondering if you also checked with this new paper orders and stuff out about it says it's going to launch into brains. So there's also a lower bound for tension on the brain.
Ah, okay. No, I wasn't aware of it. I mean, I'm sure I saw the paper, but I didn't have time to read it. I see, I see. Okay, I'll check it, thanks. It sounds very interesting. Yeah, Festina lente for membranes, all right.
Other questions? I do have one question.
Yeah.
In this, let me say, context, what do you think will be the inflaton?
The inflaton you have to put, you need to put extra sectors inside.
So, I mean, after putting the inflaton, you have to go back and check
You-
again the conjectures.
You have to worry that you are still
So
within
you're
the.
not done with this thing. You have to go back.
Or, yes, first you are done with your vacuum, and then you have to include the inflaton, and you have to worry again from the start.
Final comment. What about this Transplanckian conjecture? Do you think is correct or not?
The distance conjecture, you mean,
No,
that you cannot do large distances.
The Transplanckian, the size
The
of
TCC.
Yeah.
That one also, but yeah, the
Do you
TCC.
agree? Do you agree with this conjecture?
With the details, I don't know, but
So I think in the calculation you see that
I know.
as possible.
Yes.
So what's happening there?
Again, what is telling you there is that even if you have a de Sitter, it will decay very fast. There is some lifetime that it can have. So again, here I'm finding the same thing actually, that your de Sitter has either it does not exist because you are hitting all sorts of strong couplings, or it always has a decay channel, and that decay channel sometimes can be very, very fast. So I'm closer to the TCC, yeah, I'm closer to it.
Including the inflaton anyway in your context, in your spectrum, then you have to go again back and check the TCC conjecture.
Yes, you have to check everything. I don't know if inflation exists or not, but it's not obvious if inflation exists. I think it's a very difficult question to ask.
Okay. Thanks.
Thank you.
Thank you. Thank you.
Okay. Next speaker is Panos Betsios. Talk about inflationary cosmology from ADS wormholes.
Okay, thank you. First, I would like to thank the organizers for this very nice workshop and also for giving me the opportunity to speak here. So today I will present some work that was done in collaboration with Olga Papadoulaki in this first work, and also some more recent work that was done also in collaboration with Olga, but also with Ioannis Yalamas. So let me work. So yes, so here I present again this picture of the history of the universe. Asimina explained this picture very well in the morning. I don't think I can do a better justice than her. I will just mention that we live basically here on the right of this figure. And we observe that our universe is currently expanding. It is also hot. By this, I mean it has a non-zero temperature. And it's also extremely uniform at large scales. So today in this talk, I will be mostly focusing on the very early universe, and in particular in times before the CMB radiation was produced, so how basically everything started. So of course, any theory that we want to use to understand the primordial universe basically has to satisfy some constraints due to observational data. Those are under the name of the flatness problem, the horizon problem, the monopole problem, and the theory also needs to explain why primordial perturbations are produced that are nearly scale invariant. Now, inflationary theory is a theory that can explain all these features very well, and it also explains further features very well. So here, for example, I give you a very common plot of the tensor to scalar ratio as a function of the primordial tilt. And here I also have various inflationary models. Some of them are better, fit better the data than others, but in general, there are many of those that are pretty good. So, okay, let us assume that inflationary theory is a good theory. There are still some pertinent questions, even if we adopt the context of inflation. And these are basically questions about the initial conditions of inflation. So, for example, I will show you some typical inflationary potential of the slow roll type. And one should ask and explain why should we actually start high up in this inflationary potential and then follow some slow roll trajectory. And in particular, we would also like to understand physics before horizon crossing. And here, in the rest of the talk, basically, I will just use this star to denote basically the beginning of inflation. Of course, even if we adopt the inflationary theory, if we trace back time, evolve back in time, we still have the Big Bang, the issue of the Big Bang, that is a singularity. The universe acquires a Planckian scale, and basically our physical laws there break down. And it is natural to say, okay, you need a complete theory of quantum gravity to a non-perturbative actually to understand what happens there. But as physicists, we would like to have at least some approximate ways to at least estimate or understand some probabilities and features of the early universe cosmology. So one such proposal was given by Hartle and Hawking, and this appealing proposal is in the context of the Wheeler-DeWitt equation, and they try to understand what they call the wave function of the universe. And in this approach, basically one uses the canonical or the Hamiltonian formalism of general relativity and promotes the constraints that express diffeomorphism invariance to quantum operators that annihilate the wave function. So let me give you a few more details because maybe not everybody is familiar with this. Here I write down for you a metric of a four-dimensional space-time in the so-called ADM decomposition. With xi and xj, I will denote the spatial coordinates, and then with t, I will denote the time. So in this metric, basically you find a few more functions. By n, I will denote the lapse function, and by ni, I will denote the shift functions. And basically, then you can start with your favorite theory, let's say Einstein-Hilbert action plus some matter fields. And then if you follow the usual canonical formalism, you can write down a Hamiltonian. And then you can basically express this Hamiltonian in terms of the lapse and the shift vector, and also the metric on the spatial slices, sigma, and the momenta that are conjugate to this metric on the spatial slices. And we can also include some matter contributions. Now, since our theory has diffeomorphism invariance, basically this leads to some physical states and configurations that are independent basically of the lapse and the shift. And this leads to constraints according to the usual canonical procedure of Dirac. So one needs to set the Hamiltonian and the momentum to 0. And for example, here, since we would like to understand inflation, let's also include as matter a scalar field that we will call phi. And then if we try to quantize our theory, we have to promote these constraints into operators that basically annihilate the wave function. Now, these equations, they are appealing to the eye, but actually they have almost zero content because they're not really mathematically well defined. And okay, you cannot move much forward with these equations, but at least, as I will soon show to you, there is some truncation that is called mini superspace truncation that leads basically to better defined equations and to ODEs or PDEs in the specific case. And fortunately, since as we argued our universe is to a very good extent isotropic and homogeneous, this ansatz is physically relevant for us. So here I give you a simple version of this mini superspace ansatz. So again, we have with T, we denote the time, and then with omega sigma, we denote some slices. These we can take them to be, the spatial slices to be, let's say, spheres, if we want our universe to be compact, or we could take them to be flat or ADS. That's not very important. And then in this case, if we adopt this ansatz, basically the momentum constraint is satisfied trivially. And then the only constraint that one needs to impose is basically the Hamiltonian constraint. Now, even if we try to solve this so-called Wheeler-DeWitt equation, this PDE, we have to supplement to it some boundary conditions. Now, Hartle and Hawking basically gave one such proposal. And in their proposal, one has to go to make an excursion to Euclidean signature in the far past and basically consider metrics that are compact and close off smoothly at the past, at early times. And then the resulting state wave function, as I will show to you in a few slides, it corresponds to the Bunch-Davies or the Euclidean vacuum, which is the analog of the Minkowski vacuum in a cosmological setting when, for example, the cosmological constant is positive. Now, there are 10 alternative proposals. One well-known one is by Linde and Vilenkin. This is called the tunneling proposal. It's slightly harder for me to explain to you in such short time. But we will contrast the two proposals in a semi-classical limit that it will be more clear to you what happens. Yes?
So the fact that you end up with the resulting state essentially the Bunch-Davies is kind of a unique solution, or you can end up in any alpha vacuum, for example?
Oh, that's a good question. Haven't thought about it. In the canonical way that they studied this, you get, I guess in principle you could. So, but I don't know the answer to that question. I have to think about it, but thanks. Yes, so let me give you a simple example, empty de Sitter. So just Einstein-Hilbert action plus some cosmological constant. This admits an empty de Sitter solution. In Euclidean signature, this is a 4-sphere in 4 dimensions. And in Lorentzian signature, it's this de Sitter hyperboloid. And now, in the Hartle-Hawking proposal, basically at the classical level, we describe some complex metric, which is formed in the following way. First, you take, let's say, the S4, the Euclidean 4-sphere de Sitter. You slice it in half, and then you glue to it the Lorentzian de Sitter, the hyperboloid. Or in the complexified field space, you basically do this type of contour. So this is the classical, let's say, description of their proposal. The resulting manifold, as you can see here, is a smooth manifold. Now, let us try to understand this solution from a semi-classical or WKB approach to the actual Wheeler-DeWitt equation. Here I write for you the Wheeler-DeWitt equation. It's similar to a Schrödinger equation with 0 energy. And if you want to do some WKB approximation to these wave functions, basically you can expand this wave function in these 2 possible ways. And which expansion you would prefer, it depends a bit on the shape of the potential in this Schrödinger problem. So if you are in large A, so A for us is the scale factor, so when the universe is really large, you're basically in this region, so the potential has gone to -infinity, so the natural solutions are oscillatory. And if you are for small a, so when the universe is really small, then basically you are in this region, and since we have just 0 energy, basically you find either an exponentially increasing or decreasing solution. And then in the end, if you want to be at the semi-classical level, you also need to do some WKB matching procedure, basically at this location. Now, since, as you see here, you have 2 options, basically the no boundary proposal selects for us the increasing branch, and the tunneling proposal selects the decreasing branch. So that's basically here the 2 options that you have. Of course, you can think linear combinations of the 2 in more generality. So here you see that from this perspective, naturally our universe is Euclidean at early times, so when a is really small, and it is natural Lorentzian, or you have e to the is, which is a natural weighting factor for a Lorentzian type of action, when basically the universe becomes larger. So this dovetails well with the previous slide. Now, let us go to the context of slow roll inflation, include also the inflaton field phi, and assume we have a typical potential of the slow roll type, and then maybe you have also a reheating phase. And in this case, now the Wheeler-DeWitt wave function depends basically on two arguments, both the scale factor A and phi. And okay, what we want to do, let's say we compute this wave function at the semi-classical limit. After we have it, basically we want to compute some probability for specific history or realization of the universe by computing, for example, its norm squared. Now, let me give you some explicit expressions for the two types of wave functions, the no-boundary and the tunneling, in the case of slow roll approximation and in the WKB limit. You see that there is some normalization prefactor, and this normalization prefactor is basically weighted by the Euclidean action of Euclidean de Sitter that has the topology of the sphere, as we mentioned before. And then there is a Lorentzian piece that is oscillatory, and basically this piece depends on the on-cell action of the Lorentzian de Sitter. Now, you see that a main difference here is that there is a difference in sign, how you weight basically the Euclidean action between the no-boundary case and the tunneling case. And this sign will be very important in a while. Now, of course, here I didn't tell you what are the values that you should set for A and phi. And okay, the values that you can set are basically the values at phi star and A star. If you remember, these were the horizon crossing values that marked for us the beginning of inflation. And then, okay, you can also evolve the wave function further future in time if you want. Yeah. So you can do the matching. Yes, you can do the matching at the start, and then you can evolve the wave function and put the values at the end of inflation. Yes. So you perform the WKB matching at the start, and then you sort of.
The star value is the horizon x.
Yes, that's right. Exactly. Yes. Expanding. Yes, expanding.
The accelerator.
Yes, that's right. Okay, there was another question. So let me now, before going to the probability that there is an issue there, let me tell you first that you. Yes.
What exactly crosses the horizon?
Well, okay.
Usually it's fluctuations that cross the horizon, so it's scale dependent in that statement. That's why I got confused.
Yes.
But that depends on its momentum, right? So it's not a unique.
Yes, this is. Yes, it depends on the mode. That thing. This is basically for the zero mode in some sense, for the size of the sphere. But I agree with you that in general, if you want. Okay, so your question basically goes to this slide because you want some inhomogeneous perturbations that now can have momentum dependence or angular momentum dependence, and then you can discuss the same statement now if you include also perturbations around the spherical saddle. But that's more complicated.
Is there any characteristic scale in this language where you can compare with the Hubble?
Yeah, there is the Hubble scale.
This we know.
This we know, but additional.
Yeah, correct. We compare it just to understand the crossing. Do you have any other scale?
Well, it depends on the theory that you have in mind. Here, for example, if you just have just the scale factor, no. If you have the scale factor in the field phi, I guess maybe there is some momentum, but momentum you go to the inhomogeneities, right? To have momentum.
So you have tunneling also, so maybe the rate of the tunneling could be another scale.
Yeah, I guess so. But yeah, I'm not sure about this. But it depends a bit also. Okay, if you have, for example, the standard model, more fields, there are more scales around. So yeah, if you have more stuff, yeah. But you win. Yeah, it's okay. The nice thing about the no-boundary proposal is basically that it predicts the correct spectrum of primordial perturbations with a Gaussian suppression factor. So if you do an expansion of fluctuations around basically this spherical saddle, basically you find the usual Gaussian suppression that describes for us some analog of the vacuum. And then in the tunneling proposal, if you remember, this minus sign was a plus sign. So basically, you would find fluctuations that become unsuppressed and they grow. So from that perspective of perturbations around the spherical saddle, basically the no boundary proposal is preferred. But there is some important issue of the no boundary proposal, some hierarchy problem. And for example, you all know, of course, the current cosmological constant problem, where we basically discuss the values of phi now. But there is actually an even worse, exponentially worse problem for the no boundary proposal, because if you remember this probability that you were computing with the norm of the wave function squared, basically is weighted with a Euclidean axion. And then if you compute this in the WK limit, you basically find this sort of WKB expression. And if you read this equation, you see that basically you find an overwhelming probability that is much, much larger than 1, that basically this V is as small as possible, so that this exponent becomes as big as possible. So this means that your universe would prefer always to be there at this point, and it has really a negligible, close to 0 probability of being here. So basically, the no boundary proposal predicts that basically you have the least number of A-folds. It's exponentially improbable for your universe to have started up here in the potential and basically have followed the slow roll trajectory. And this issue basically stems from the fact that the Onsel axion for the positively curved Euclidean de Sitter is negative. Yes?
Okay. Can I make a dumb question, because I don't really do cosmology? Is it
Yes.
a problem if it's exponentially improbable that you start in an inflation phase, because you only need that to happen once?
Well, I agree. If you cannot really say I will perform the experiment of having the universe evolving many times and comparing this, but it is, we would like somehow, okay, strictly speaking, I cannot say that is a 100% mathematical problem, but it would be nice if our theory would naturally predict for us that it is actually quite probable for us to have some long period for inflation, if it's allowed by our theory. I view it at least in this context, this way. So,
What does this predict for ADS?
very good. So now we go to ADS. The no boundary proposal in the case of ADS works perfectly well. So the analog of the no boundary here is the regular interior of ADS. Here I just draw for you ADS as a ball. So its boundaries are S3s, and this is the metric for, let's say, ADS4. And in this case, basically, the Onsel axion, if you perform carefully the holographic renormalization procedure of Kostas, Dimitris, and many other collaborators, basically you find a positive axion after doing this holographic renormalization. So e to the minus s is naturally less than 1. And then you can expand in fluctuations around it. So you find a well-defined probability. You can also match it with some CFT results if you have some dual CFT, either in the semi-classical limit, or even you can even do more than that if you have some supersymmetry, like in ABJ theory, for example. You can have even finite N or finite G Newton corrections, and everything works very well in this case.
If I put V negative in your previous formula, that doesn't seem to give the same answer.
Well, V negative wouldn't be this case, right? For V negative, in general, you would get ADS, right?
Yeah, so for example, suppose this potential went a little bit under the line.
Okay. This formula is okay. So this formula only holds if V is always positive. Well, it's derived under this assumption. There are some assumptions for deriving this formula. If V is negative, I'm not really sure that this holds. Maybe you need to put some absolute value. So, okay. I know that this formula holds only when V is positive in this context here. So I'm not sure that this formula holds when V is negative. Okay. But the issue here is that in this case, this example does not have any direct relation to cosmology. And by this, I mean with a simple analytic continuation, tau goes to IT, as in the no boundary proposal. Of course, as both Elias and Kostas, there are many examples of that people have tried to work in the context of ADS-CFT and understand cosmology, like brain worlds, or domain wall CFT correspondence, or DS-CFT correspondence. I don't have time to review all these things here. I will just focus on something very specific that can be more cleanly related, let's say, to the usual no boundary case. So let me now go to that context, and this is ADS4. ADS4, and the boundaries are RS3s, omega 3. Okay. So this context that can be related to cosmology is when you have manifolds that look like wormholes with two Euclidean ADS asymptotic boundaries. So in these manifolds, basically you find the scale factor that grows exponentially on two directions. Let's say tau goes to plus minus infinity. And then perhaps here in this picture, it has some minimum, let's say in this time reflection tau equals 0 line. Now, if you have such Euclidean wormholes, these are not related to black holes. But for example, if you perform some analytic continuation, tau goes to IT, like in the no boundary proposal, basically you will find a manifold that looks like a big bang, a big crunch universe. Of course, remember that here we, again, still have lambda to be negative, right? You cannot really have an exponential expanding universe. And so here it's the Lorentzian metric, and then basically the fact that the scale factor had a minimum in the Euclidean section translates to the scale factor having a local maximum in the Lorentzian section, and then it crunches. Now, an issue, as I mentioned, with this manifold is that basically they don't allow any period of inflation, right? So what was our idea? Our idea was the following, was to ponder whether it is actually possible to combine features of both de Sitter and anti-de Sitter, and basically have a picture like this here in the middle. So in the left, I show for you the Hartle-Hawking proposal. So this is just de Sitter. Here I show for you the analytic continuation of these wormholes that leads to crunching geometries. And here I show for you something like an Euclidean ADS wormhole that shrinks, and then it locally expands near the throat, and it resembles this left image. And then this has a chance of, when you analytically continue, to be possible basically to describe something that is expanding instead of contracting. So that's the general idea. Of course, people had thought about something similar, let's say, in flat space in the past. So these are the only references that I know. They're from the 80s, the first ones. And okay, we call these wine glass ADS wormholes, basically because of that sort of shape. And okay, some other people also have thought about similar nomenclature. And the defining properties for us is that the space is a wormhole. It has two Euclidean ADS asymptotic boundaries, but then the scale factor has a local maximum in the throat and not a local minimum. Of course, as I mentioned, these are good initial conditions for an inflationary evolution. And of course, if you want to support such solutions, you need some scalar potential that is more involved, right? It needs to have both some positive and negative values. So here, I give you an example. Don't take this, for granted that this is the only example. This is just a simple example as a toy model, as an EFT toy model that can realize our proposal. So let me now go to an explicit model that realizes the proposal. So consider, for example, the Einstein-Hilbert action with an inflaton field. And then you can add also some radiation or some additional matter. So this matter, for example, could be also an axion, et cetera, et cetera. And then if we try to find solution with the spherical, symmetric, and homogeneous ansatz, basically we can reduce the Einstein equations and the scalar inflaton equations to this set of two equations. Of course, there are more equations that need to be solved for the axions, for any radiation, maybe some gauge fields, et cetera, et cetera. And in this case, there are examples of wine glass wormholes, and we studied basically two main cases. One is the axionic case, and the other case in the more recent work is basically when you have a magnetic type of radiation. And for us, it is important also to notice that if you have magnetic fluxes or magnetic radiation, basically in Euclidean signature, this rho of radiation is negative, basically because the stress energy tensor in Euclidean signature is E squared minus B squared. So there's a relative minus sign here. And this is very important because you see the axion also has a plus sign here. So it's important also for this to become a plus to have such solutions. So it could be from anything. For example, it could be some U1 gauge field, or with Elias we had studied some SU2 gauge fields. Yeah. So here I try to be general. Of course, we have explicit cases and explicit solutions, but yeah, it's a general feature.
Just another question.
Yes.
Why action is 1/8 to the 6?
this is how it scales. It's like stiff matter. It behaves like stiff matter. It's massless, and it's also like a two-form. Well, you can dualize to make it a scalar, but it starts as a two-form field with a three-form. And then, the conformal invariant radiation basically gives this 1 over a to the 4. So, but yeah, these solutions are more general than what. I assume more minimal. I will give you an example where there is some non-minimal coupling. It's important for the context of Higgs inflation. I will also go to that. Yeah, very good. So let me skip, because of shortness of time, the details. So there are such solutions. Basically, you have to play with the fact that there is some kind of friction term in the scalar that can be anti-friction depending on the sign of A prime, or how the manifold shrinks or grows. And then basically you can find the solutions. You can see the details in the paper. That's not very important. What is important also is, if we want to have some inflationary region, is also to have some slow roll region in our potential, not only to have some negative region. And by playing a bit with the potential, of course, we are bottom up. You can tune a bit the potential such that you can accommodate various options that are consistent with experimental constraints on inflation. And these constraints basically constraints for us mainly this region of the potential, not so much that region, the Euclidean region of the potential. So let me give you a quick flash on how we evade the issue of the no-boundary proposal. We can evade this issue basically because now we have ADS boundary conditions. Of course, we have to do holographic renormalization, but basically the ADS boundaries, since V is negative, give a large negative contribution here. So this becomes positive with this minus sign. We also have some positive contribution here from the matter or radiation, action or radiation present on the background. And we found that basically the action is positive. And that's good because we have a well-defined probability, like in the usual ADS-FT examples. And basically, we can evade this issue of the no-boundary proposal. And actually, we found some trajectories that since you solve. It's important to mention, I forgot to mention that in Euclidean signature, basically, you solve the equations in -3 in the inverted potential. So basically, you can find classical trajectories that stop precisely at the minimum of the inverted potential, which is the maximum of the canonical potential. So basically, you find trajectories that are for which it's cases for which it's extremely more probable to actually start inflation up here, up in the top. So in this case, we basically evade this issue of the no-boundary proposal, and then we can inflate in the usual way as in other models. So let me now, before closing, mention the more recent model that we have that is more consistent with experimental data and observations. So in order to do that, basically, it's a problem, right? You need an inflaton field. So what is the inflaton? Why we haven't observed it, or what is the inflaton for us? And there is a proposal, such a proposal for the inflaton, and this proposal goes under the name of Higgs inflation, where you identify the Higgs boson with the inflaton. So in these models, as it was previously mentioned, you need to include also some non-minimal coupling for these models. There are also some generalizations of the Starobinsky model. You can think of them in this way. And of course, these terms also appear when you consider loop corrections and the effective action. And it is also, so up to now, I have explained for you how we can embed the inflaton, let's say, in our standard model, but I haven't explained to you how you will get a potential that has both a positive region and a negative region. And to explain the fact that there is also a negative region that is needed in our proposal, I have to mention also that current experimental data for the Higgs and the top mass favor the so-called Higgs standard model metastability. So basically, one can show that for central values for these masses, typically you get a potential that turns negative at a certain high energy window. And since it turns negative at a certain high energy window, of course now there is the question, because there might be additional particles as you go to the UV, perhaps you have supersymmetry, or perhaps you have other particles, etc., etc. So of course the shape that I draw here of the potential at high energies should be taken with a grain of salt because we don't really know what happens at very high energies. But if we accept the scenario of Higgs metastability, basically there will be some high energy scale where the potential will be negative. And then if you go back to Einstein frame, basically you find an effective potential that has this form. It has the usual phi to the fourth type for small field values. Then it becomes more flat at some intermediate inflationary scale, and then it becomes negative at some high energy scale. And if we combine, let's say, all these features of this model, basically we can get a model that is consistent with current experimental data and also can realize our proposal to have both a Euclidean phase and then basically to have a slow roll phase towards the current era. Now I have some future directions, but I will skip these future directions because I think I don't have time. So let me just summarize what we did here. We proposed a new type of wave function for the universe that is computed from the gravitational path integral with asymptotical Euclidean ADS boundary conditions. Now in the semi-classical limit, it describes some Euclidean ADS wormhole or half wormhole. And then if we slice it, we can glue to it some Lorentzian manifold that is expanding and inflating. And our proposal can be realized when we have a non-trivial scalar potential that has both negative and positive, takes both negative and positive values. We also saw a specific realization in the standard model plus general relativity in the context of Higgs inflation. And it evades some issues of the no-boundary proposal. We have some well-defined probabilities. And also, finally, let me mention that it raises also some interesting possibility of describing the physics of such inflating cosmologies within the context of holography. But to understand this, we need to understand better the duals of Euclidean ADS wormholes. And also, of course, I don't know if these potentials, as the ones that I drew here, are in the swampland or they can be actually realized in string theory. But that's, I think, an interesting question for the future. And with that, I'd like to thank you.
Short questions.
I have a question. Probably it will sound a bit weird, but when we have the Einstein equations for cosmology, we supplement them with the equation of state, which relates the density and the pressure.
Yes.
So in there is this coefficient W.
The barometric radiance.
Yes.
Which we, depending on the era of the evolution,
Yes, it takes
various
different values. Yes.
I was wondering if we can reformulate the problem as a problem of initial conditions in your equation of state.
Well, in our proposal, we don't have any problem. This problem of the no boundary is not there. You mean about the usual?
Not necessarily. If there is any
More general.
ideas or thoughts that...
I guess so, but I don't think that as long as you demand a potential that is positive everywhere, and you start, well, it looks like the one that Hartle and Hawking took. I don't think that you will find some solution to that problem, right? You will just rephrase the problem in different language. But maybe if you again, allow the possibilities that we mentioned in our work, maybe then you can resolve it again. But it will be a rephrasing for sure of the same problem. But it might be interesting to do. Yes.
2 points. The first is that although you started with a no-boundary proposal, you gave us a boundary proposal.
Yes, that's right.
Therefore, you have many initial conditions in principle you can put. Any comment on that?
Yes, I have a comment. So currently we are working on understanding the perturbations around our saddle. And you see, we want to find something that is for which both the probability is well defined, but also for which also the fluctuations look like the fluctuations that are produced in the usual inflationary scenarios, and they look reasonable. And in order to do that, at least preliminary research, we haven't really finished the computation, looks like we have to pick the Euclidean vacuum near the ADS boundary. So that's the boundary condition that we have to choose. Because here you see in ADS, for example, you can insert sources, right? Or you have more options.
Well, the vacuum will be always ADS eventually to go to the boundary.
Yeah, but
the question is what happens after. How the probability depends.
I agree. It looks okay. Preliminary results, they are not yet finished. Look like since the geometry here near the throat looks like a sphere. If you choose the Euclidean vacuum here near the Euclidean ADS, and okay, this is not really pathological, very narrow or very weird, then it looks like the fluctuations that you will produce, let's say, at this tau equals 0, they will look similar to the fluctuations that are produced by picking the no-boundary proposal. Quite similar, but that's again preliminary. But that's a very good question. I agree with you.
My other question is very general, because in the past, this type of Wheeler-DeWitt way of deriving wave function of the universe has been criticized. How is it possible an equation which is kinematical, because it's isomorphic invariant, can give you dynamical information?
To give time. Okay. So for us, okay, I started the motivation from the Wheeler-DeWitt, let's say, perspective, because I wanted to mention mostly the Hartle-Hawking. But what we've done so far is mainly the semi-classical regime. So we just did what also Kostas did in his talk, etc., etc. So, you know, Einstein-Hilbert action plus fields plus fluctuations. So we didn't really solve at any point the Wheeler-DeWitt equation, actually. We just used it in order to motivate the issue with the no-boundary proposal. Of course, it would be very interesting, I agree with you, to understand the Wheeler-DeWitt equation in the context of asymptotical ADS spacetimes. People have worked on that. But I don't know many results that are, you know, very concrete. I mean, in low dimensions, you can do many things, 2 and 3 dimensions. You can really understand. We have some models, for example, with Olga in 2 dimensions, for which there exist dual matrix models, like matrix quantum mechanics, and there you can compute the Wheeler-DeWitt wave function exactly to all orders, even in G string, etc., etc. There you can make things very precise. But in 4 dimensions, I totally agree with you. Yeah, we can have more discussions afterwards. It's really
Other questions?
I have another dumb question. So your wine glass geometry looks a lot like, if you take the limit where the neck of the glass is really thin, looks a lot like it's going to give you the no boundary proposal. So I was wondering, is there a state on the Euclidean ADS that you can insert as an initial condition that will actually give you the no boundary one?
Yeah.
And is that state special?
Yes. I don't know if it's exactly what you want, but there was a paper by Hebecker after our paper where they were trying basically to excise some region here and basically put some kind of brain there. But of course, it's a brain in time. Like it's like, I don't know, people were calling this, I don't remember, like eye brains. I don't know. There was some. I don't know if these brains exist. First of all, in strict theory. But yeah, people have thought about like stopping, let's say, the space-time at some point and putting some brain and then some conditions and then some state there.
Yeah, but I'm asking about your model.
Well, in my model, what would you want? To just cut it off?
Just what you have on the slide. So just took this is Euclidean pinches and then joined smoothly the no boundary.
Yeah.
That's really what's happening. You just take, you prepare the Euclidean ADS like on the right figure.
But that's, yeah, exactly. This limit is a bit pathological, right? You cannot
It's
really.
pathological because you got the zero sides.
Exactly. Yeah.
But what's the state on the right? That's which one is that? That's the tangent one.
You mean here? This is the no boundary. This on the right is basically you had a Euclidean ADS wormhole, and you didn't have any positive cosmological constant, right? It would just crunch. Symmetry is different. Yes. Yeah.
Yes. But if I understand well, this scenario works only for the case of string with single grid equation, strictly with single grid. So Higgs, these grids complex fields has also aggregation, so it cannot stop the black hole, will it? It will waterfall.
It will open. It will open.
That's my impression. I don't know. Don't calculation, but this is my impression.
I haven't thought about it. It's a good question. I haven't thought about it, to be frank. I don't. Yeah. The complaint is that, well, basically, if it's not just a single scalar field, but it has more components, right? These are the Goldstone modes.
They are massive. The other ones are also modes. But usually it's a value. I mean, you just if you integrate out the other directions, it goes effectively. You discard the evolution of the value.
Yeah. So okay, the problem is, for example, because you see, we want a potential that has both a negative and a positive region. I don't know what happens in our context, right? I can understand what happens here. Let's say close to that point, which are Goldstones, etc., 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 right? For the Higgs. But yeah, well, if you include also the running, right? I don't know. I don't know the shape. Yeah. you are always in the broken, so yeah, it's okay.
By the way, you don't need actions, whatever, all the other stuff just to get this potential. So whatever you mentioned, for the other stuff is not relevant to this potential, right?
The other stuff are not relevant for the potential. They are relevant if you want to have this type of bounces, right? To make the wine glass, you also need some kind of fluxes so that the thing doesn't really pinch off, right? Because if you didn't have the fluxes, basically,
You don't have this,
where's the picture? Basically, if you don't have the fluxes, this thing would like to pinch off there, right? In this neck, it would like to close. So the flux is basically what is presenting this for closing. But experimentally, that's fine. And basically, it would be nice to have magnetic fields. We have magnetic fields. They get diluted very much during inflation. So there are no experimental signatures from this. But yeah, current.
Other questions? Okay, if not, let's thank Panos again. So the last speaker of this session will be Boris. Bruno will talk about shadow formalism for supersymmetric conformal blocks. Okay.
Thank you. First of all, I would like to thank the organizers for this extremely illuminating workshop and for giving me the opportunity to speak here. And today I'm going to talk about shadow formalism for supersymmetric conformal blocks. My talk will be, I'm afraid, somewhat more pedestrian than previous ones, but maybe it's not too bad for the last talk of the day. Let's start. The story deals with conformal field theory. I believe many of you are actually quite familiar with that, but just to be safe, I'll give a very quick recap. To be more precise, I'm interested in CFT in 2 dimensions. You have some peculiarities. So usually you have a global conformal group generated by shifts, rotations, scaling, and special conformal transformations. In 2 dimensions, you have additional symmetry. Basically, any holomorphic function gives you a conformal transformation. So there are infinite number of them, and they form this nice Lie algebra. The generators form this nice Lie algebra known as Virasoro algebra. Well, actually, I'm only talking about this to later say that we don't really need it. But anyway, this parameter here is the central charge. And in my talk, I'll be mostly interested in the limit of very large central charge. OK, so in CFT, the key object is a primary field. That's the field that has tensor-like transformation properties. And
there is a state operator correspondence. And probably what's also important is that what's probably I have to mention that the global conformal group in this case is generated by just three generators, L0, L1, and L-1. So it's isomorphic to SL2. So conformal symmetry, actually even global conformal symmetry, imposes quite serious restrictions on correlation functions of primary fields. So basically 2 and 3 point functions are fixed exactly up to a constant. By convention, we normalize 2-point function to be to have a coefficient equal to 1. And the many point functions are actually, you can they depend on n-3 invariant cross ratios. So there is a prefactor that is that ensures the symmetry under transformations, and then there are some arbitrary, generally speaking, function of invariant cross ratios. So as I said, this story is about conformal blocks. So what are conformal blocks? Conformal blocks are basically the functions that appear in the expansion of many point functions, in particular 4-point function. For your primary fields, you have some OPE, and this OPE is basically the operator product expansion is an expression of product of local operators in terms of your primaries and their descendants. And it turns out that you can separate the sort of dynamical information encoded in these 3-point constants and kind of kinematic information, which comprises the conformal block and which is essentially model independent in the sense that it depends on conformal dimensions, but doesn't depend on well, it depends on conformal dimensions of the fields in your correlation function, and also on conformal dimension of the intermediate field, which appears here in the expansion, but it doesn't depend on structure constants. So conformal blocks are obviously very important for bootstrap program, since basically bootstrap equations are written in terms of these conformal blocks, and if you know the conformal blocks, then you can use a bootstrap to restrict or even find, in this case, your structure constants. Okay, so I'm, however, interested in the semi-classical limit, the limit of the large central charge. And it happens that in this limit, actually, you don't need to care about these higher Virasoro generators because the constant, the coefficient beta IGP, which appears in the OPE, actually vanishes in this limit unless the state is just a product of action of several derivatives. So all the descendant fields involving higher generators actually don't contribute to the OPE and therefore to conformal block. Semi-classical, well, obviously they are not as interesting objects as the full conformal block, but still they have some applications. In particular, they are known to be dual to geodesic Witten diagrams in ADS3. Anyway, knowing conformal blocks is a important problem, and even if you know only semi-classical limit, it's already a start. For this purpose, there is a technique known as shadow formalism. Originally, it was proposed for scalar fields in dimensions greater than 2, and later was generalized for fields with non-trivial spin, and then for d equals 2. So how does it work? It works, the key ingredient is this shadow field. It's the quasi-local quasi-primary operator, which oh, apologies, there you should have 4 minus 4h, but anyway, it's given by this integral of some primary, actual primary, local primary with this kernel. And what's important that you integrate over the entire space, not just over the holomorphic coordinate, but over all the conformal plane. The conformal dimension of this expression is 1 minus h. And it turns out that it's sort of conjugate to the original field because its two-point function with the original primary is two-dimensional delta function. Yeah.
Is this realizing the conjugate representation?
Yes. Well, here the caveat obviously is that it is only well, as long as we are talking about d equals 2, it's only really true in this semi-classical limit, because if you this expression, it's well, actually this is true everywhere. But what I'm going to tell you later, it's going to depend heavily on this large C limit. So yes, that is actually true for any C, but this now we want to construct some sort of projector operator, pH, which is given by this expression. And we want to decompose identity in terms of this pH, and it well, this property is self-evident from this expression. However, if you start to involve the higher Virasoro generators, all the scheme starts to break down. But in the limit of large standard charge, you can decompose the identity in terms of such operators. This was like result of 2018, and what we did, we generalized it to an S sector of n equals 1 two-dimensional SCFT. And again, here's some brief recap of what's this beast. So you have some superspace C11, and it's parameterized by these coordinates involving one complex number and one Grassmann number. And it's useful to introduce such analog of intervals so that this expression actually scales in the right way. And then you introduce superderivatives, and you tell that your superconformal transformations are transformations that preserve this derivative. Again, there is a global subgroup which is generated by Virasoro global subgroup, but also by generators G1/2 and G-1/2 fermionic generators. So the algebra, the full algebra looks like this in this case, but again, we only actually need the global subalgebra. And the SCFT works as follows. You have super fields, which generally have like 4 components. The bosonic component well, each component is a Virasoro primary in its own right, but with respect to the full super Virasoro, that's a single supermodule, and the conformal dimension of phi small is h, and then conformal dimensions of other components are differing by 1/2, and this last component has conformal dimension h plus 1/2, h plus 1/2. Again, superconformal symmetry restricts the shape of the accretion functions, and you can write the two-point function as follows, where this expression has to be understood as a Taylor series expansion in Grassmann variables. And you have now two kinds of invariant cross ratios. Even one, which is basically the same as in bosonic case, but also you have odd one. And the three-point function now involves two independent structure constants, and this second constant goes in front of the term proportional to eta bar. And it turns out that in this case we can again construct the analog of shadow operator, and it's given by integral over the whole superspace, similar integral, but it has now the difference is the dimension of the shadow field. In this case is 1/2 minus h instead of 1 minus h we had in the bosonic case. With some computing some integrals and introducing some regularizations, actually it's probably worth mentioning that this integral is as written, it's not convergent, so you need to introduce some sort of regularization. It was also the case for the bosonic version of this formalism. But at the end of the day, you can demonstrate that the two-point function for this operator with the original one again factorizes in the product of delta function over spatial coordinates and delta function of Grassmann coordinates. It doesn't matter actually. I mean, actually, likely not. I mean, you are considering large C. Actually, yes. I mean, formally, you are right. I mean, again, well, this integral actually is not convergent for any h, to be honest. But you can regularize it, and the relevant part actually can be continued analytically to h. You can do it by plugging here, instead of h, you put here h minus epsilon. And then you can continue analytically in epsilon. Well, yes, so obviously it makes most sense for h for h, within certain limits here. But probably the right way to think about this is that this particular integral representation is indeed correct only for certain conformal dimensions, but the shadow operator itself admits some analytical continuation in H, so that you can still get this kind of delta function identity for the two-point function. Okay, so it's as previously we construct the projector operators. It's given by almost the same formula, except again you have integral over the whole superspace now, and also I need to mention that the structure constants, the three-point constants involving one shadow field and two primary fields are obviously not independent, but can be expressed in terms of the structure constants of the primary fields. But the trick is that the sort of even structure constant for shadow field is proportional to the odd structure constant of primaries, and vice versa. But now we would like to actually use this formalism to compute the superconformal blocks. Well, the first obvious example to test our formalism is this 4-point block. It can be, generally speaking, decomposed as follows. You have some lag factor, again, ensuring the invariance on the global superconformal symmetry. Obviously, it's not unique, but we have chosen it in this way. And then you have some function g, which depends only on invariant cross ratios, and you can expand it in Grassmann variables like this and compute separate terms in this expansion. So to compute them using shadow formalism, we insert this identity decomposition into creation function between phi 2 and phi 3. Then you will have a representation of your 4-point function as a sum of these conformal partial waves, where each conformal partial wave is given by this integral, and these v's here are just 3-point functions. 3-point functions involving the original primary, and this one involves the shadow. Important observation here is that this conformal partial wave actually includes contribution not just from the conformal block corresponding to intermediate field of dimension h, but also to from conformal block corresponding to dimension h star of the intermediate field. So there are two contributions, and to separate them, you will need to consider the asymptotics. So here are some results. I mean, to extract the lowest component, you just set all the Grassmann variables to 0, and then the integral can be evaluated. It's not that difficult. It boils down to some bilinear expression in hypergeometric functions of x and x bar respectively. So here it is, and obviously you can separate the contributions from this one and from this one by again examining the asymptotics of individual terms in this expression. So at the end of the day, thanks. At the end of the day, you will have these sort of expressions. So that's just to give you example of how these answers look like, and they look like just hypergeometric functions. Actually, not that different from results you would obtain from minimal models for some reason, but again, that's a completely different situation. It's large C limit, but anyway, surprisingly, this result looks somewhat similar. The last topic I would like to address today is the application of shadow formalism to evaluation of creation functions on a torus. In this n equals 1 SCFT. So creation functions on a torus, they are already somewhat more complex. So they even well, you have now even one point function is somewhat non-trivial quantity, and they involve a super trace over the subspace over a submodule of weight delta 1, and then sum over all these delta 1s. So for anyway, you can still do the same thing as you did on the plane. So basically, you can insert, for example, here or here your supersymmetric shadow projector operator, your identity decomposition, and this will split your creation function into a sum of conformal partial waves. And the representation of these conformal integral representations for these conformal partial waves you will obtain, they look as follows. The funny thing here is that you will get this frequent function which depends on q times w1, and this q times w1 is actually I mean, it's not really a product, it's a notation that says that you basically scale your coordinate w1 by q, so that the the complex component is multiplied by q, and the Grassmann component is multiplied by square root of q. And it obviously can be also decomposed into a sum of conformal blocks. And the same can be said about two-point function. Well, two-point function is more complex, so I didn't have the space to write all the components, but you can just consider some components, and they also admit expansion in terms of these superconformal blocks. Okay, so that's basically how the answers look like for one-point blocks and for the two-point blocks. So that's basically the story. I mean, I don't think we should delve into the details of this computation, but at the end of the day, you will get these expressions. Obviously, you can also get all the other components for that. I mean, if you are interested, please check out our paper. But that's basically all I want to say for today. So to quickly sum up, the shadow formalism admits a generalization to this n equals 1 SFT, and it is a useful technique that allows to comparatively easy computation of creation functions and conformal blocks in this large C limit. And we even got some new results, like the result for two-point block was previously not published to the best of our knowledge. And well, there are some obvious directions into which you could expand this work. So we are interested in generalization of this picture to Ramon sector as well. And also it's interesting about what is the dual description from the CFT perspective for many point superblocks. And the final question, which maybe it's not really answerable, but it would be interesting to see if you could extend this formalism to like compute 1 over C corrections. It's not going to be that easy actually, because if you look at this argument, then you will see that, well, actually the structure of terms of the order 1 over C is quite more complicated than what you have in the leading order. But anyway, that's an interesting question to consider. So thank you very much.